I'm going to find conditional distributions from the PDFs rather than CDFs. I think it's easier. Your book does it from the CDF perspective, which I find more cumbersome. But if after looking at this, you think that might be more useful, you can look at it, go through this way first. So some definitions, just recall that a marginal distribution, if we have the joint, so if I have F as the joint distribution, marginal distribution, we integrate out one of the variables. So if I want the marginal distribution of X, we're going to integrate Y for all values of Y that are reasonable. Same thing the other direction. If we want the marginal distribution with respect to Y, we integrate out the X for all reasonable values of X. So then the conditional distribution. There's no good notation, as discovered throughout this course, right? There's not nice notation for most of this stuff. But the idea is I am looking for a conditional distribution of one variable where I know something about the other. So if I want the conditional distribution of X, given I know things about Y, it works similar to conditional probability, where we have the probability of the intersection, so we want the joint, divided by what I know things about Y. So I'm going to divide by the marginal distribution of Y. So again, this is for the PDFs. So if I know the joint PDF, I can divide by the marginal distribution of Y. That will give me the conditional distribution of X given Y. Of course, you can flip it around. If I want Y, and given that I know X, I'll divide by the marginal distribution of X instead of Y. Okay, let's see how this works. So from class, we have this joint distribution, 6x plus times y squared on the unit square. We found that the marginal distribution of x was 2x, marginal distribution of y is 3y squared. So let's find the conditional distribution. Remember, conditional is always joint, so both, divided by the marginal that I know. So for the first one, I know y. So I'm going to take the joint, which is 6y squared, 6x, y squared. And I know y, so I'm going to divide by the marginal distribution of y. And we end up at 2x. The other way around, I start with the joint distribution. I now know something about x, so I'm going to divide by 2x, the marginal distribution of x. And we end up at 3y squared. So that's how we go about it from a PDF perspective. Now you may also look at this and say, hey, we got 2x and 3y squared. That's kind of where we started. And that's the other side of this piece. That's independence. We say that random variables x and y, these are continuous random variables, are independent if they're joint PDF. We multiply their marginals together. And we alluded to this in class as well. So if this is true, we would say that x and y are independent. Now, there's also a lemma which says that our conditional distributions are equal to the marginals, then we're independent as well. So whether we're using the marginals multiplied to give us the joint, or we're using the fact that the conditional distributions are the same as the marginal distributions, that would also imply that x and y are independent. So the example we had just a minute ago of g of xy equaling 6xy squared, where we had that the conditional distribution of x was 2x, and that was also the marginal distribution. And then the same with the conditional on y was 3y squared, and that was the marginal as well. We can use that to say that x and y are independent. All right, let's look at a different example. Let's say x and y, or f of xy, the joint PDF is x plus y. We'll stick with the unit square just because that's a nice region to deal with. So that's our sample space. We want to determine if these are independent. So go ahead and, at a minimum, try to figure out the conditional distributions. So our marginal distributions, if I want the marginal with respect to x, I'm going to integrate out the y on 0 to 1, x plus y dy. We get down to x plus 1 half. Marginal for y is y plus 1 half. At this point, you may already feel like you can say they're not independent. Because if I multiply these two marginal distributions together, we do not get x plus y. But we could also look at the conditional distributions where we end up with x plus y divided by, I know y, so y plus 1 half. And the other one, we get x plus y divided by x plus 1 half. And so our conditionals are not equal to our marginals. So definitely not. So x and y are not independent. How does that play out? Well, if they're independent, if I'm looking at the probability that x is less than a half, given that y is 0, that should be the same if I'm given that y equals 1. It shouldn't make a difference which one I have, but it will. But we can actually figure these probabilities out. If I'm looking for x is less than or equal to 1 half, I need to integrate x from 0 to 1 half of my conditional distribution, because that's the probability I want. So I'm going to look at f of x given y equal to 0. I'm going to integrate with respect to x. So I'm going to get 0 to 1 half of, well, I have x plus y, but y is 0. And then I have divided by y plus 1 half, so 0 plus 1 half. So I have the integral from 0 to 1 half of 2x. We integrate that to x squared from 0 to 1 half, and we get 1/4. Go ahead and try the second one. All right, so for the second one, we're still integrating x from 0 to 1 half because I want x up to 1 half. I'm still know something about y. So I'm still looking at the conditional distribution of x with respect to our given y. But instead of zeros, y is now 1. So we end up with x plus 1 over 3 halves x. That will integrate to 4/3 x squared plus 2/3 x from 0 to 1 half, which will end up at 2/3 overall. Not the same value. And it should be if they were independent.